Hi and welcome to my video on Kirchhoff's laws. Let's get started. So what are they? Kirchhoff's laws are two rules concerning circuits that allow us to solve complex circuit problems involving multiple circuits. They allow us to create equations for the circuits to better learn how the electrons are flowing throughout. An important thing to remember is that they are only applicable with closed circuits. Let's go over the first law. The first law is called the current law, which states total current or charge entering a junction or node is exactly equal to the charge leaving the node, as it has no other place to go except to leave, as no charge is lost within the node. In other words, current in must equal current out, even if it is being split up. This law leads us to the understanding of conservation of charge, because there cannot be a randomly created charge in the middle of the circuit. Everything must even out. So, an equation for Law 1. The way to compose an equation using Law 1 is to find the junctions of the circuit, assess what is going in, and set it equal to what is going out. For example, let's look at this junction. After looking at the directions of the arrows, we can create an equation stating that current 1 is equal to current 2 plus current 3 plus current 4. And we must know this because what goes into the junction must equal what goes out. 2, 3, and 4 are leaving, so they must be equal to current 1. Now let's go over the second law. Kirchhoff's second law involves voltage instead of current and states in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is also equal to 0. Basically, the sum of all voltages in the loop must equal 0. Like the first law, this one involves conservation as well, but in this case, it is conservation of voltage. The way to compose an equation using Law 2 is to separate the circuits into loops. Doing this allows you to separate the different currents and resistors throughout the circuits. Now let's assess a circuit that only has one loop. We know that voltage change across the circuit is equal to 0, so a way to write this would be the voltage of the battery minus the total voltage of the circuit is equal to 0. Further, because we know that resistance times current is equal to voltage, we can substitute this in for the voltage of the circuit. So E minus I times R is equal to 0. And when we plug this in, we see that it equals 0. And also don't worry if you're concerned about how loops work. The practice problem that we go over will involve this. So now let's apply these laws to a circuit. This is the best way to practice using these laws to solve problems. So here is the problem, which we can find in our physics homework number 4, question number 6. We are asked to find the values of currents 1, 2, and 3, and then to determine the direction of the flow of current 2. Why are we asked to find the direction of current 2 if it already has an arrow? It's important to realize that the arrows that we write are ambiguous. They don't tell direction and simply represent the presence of a current. We'll have to figure out the direction through applying Kirchhoff's laws. A good place to begin is listing out what we know. E1 is equal to 10, E2 is equal to 25, resistance 1 is 15, and resistance 2 is 20.6. So what we don't know is the values of all of the currents and the direction of current 2. So now let's map out our loops. We'll label the left loop as 1 and the right loop as loop 2. Now let's consult our laws. Which one could be of use first? Using the current law, we are able to map out the incoming currents in comparison to outgoing currents. So we can use this one first. Current 1 is equal to current 2 plus current 3, because we can look at the junction. What goes in must equal what goes out. So current 1 is equal to current 2 plus current 3. Now let's try to make a few more equations to solve the problem. Through the voltage law, we know that total voltage across the circuit must equal 0. So let's apply this to loop 1 first. We know that loop 1 involves E1, I1, R1, I2, and R2. So ideally, we could write that the total voltage minus the voltage of 1 plus voltage 2 is equal to 0. Or E1 minus voltage 1 plus V2 is equal to 0 because we know that voltage total across loop 1 is E1, or 10 volts, according to the problem. So now let's try to solve for voltage 1 and voltage 2. We know that voltage is equal to I times R. This can help us to apply this rule, as we can then write a full equation to represent the loop replacing voltage with IR, or with the IR of each section. Current 1 and resistance 1 multiplied together are equal to voltage 1, and current 2 and resistance 2 multiplied together are equal to voltage 2. And this gives us the final equation of E1 minus I1 times R1 plus I2 times R2 is equal to 0. So now let's go over loop 2. We know that loop 2 involves E2, I2, and R2. We can also see that there is an I2, but for all intents and purposes, this label is irrelevant to loop 2 because there is no junction for it to cause a problem. For this loop, we can do the same exact thing we did for loop 1. An ideal equation would be E2 plus I2 times R2 is equal to 0. Now, this equation contains an important difference from the way we compose the first loop's voltage equation. Why do we write a plus sign for loop 2, but a minus sign for loop 1? This is because, according to how the loop was drawn, current 2 is flowing against the natural current of the loop, and although the directions of the currents are ambiguous, we need to solve for them, and solve for them how we write them in order to have accurate equations. This may be confusing, as I said the current directions don't matter, but now they do. To better explain, we don't actually know the direction of any of the currents just by how we draw the problem, so we can't assume any direction through just the diagram, but the way we draw it influences the way we set up our equations, so we need to keep the directions in mind until we reach the end of the problem. This may become clearer once we are done, so just hang on. So as of right now, we have 3 equations. So let's start plugging in numbers to see what we can do with our new equations. Because we know E2 and R2, we can start with our equation 3 to solve for loop 2 first. Note that this negative value is an indication for the direction of the current. Because it is negative, it means that it is flowing in the opposite direction that we labeled it. This means that the direction of current 2 is actually going upwards. Now that we know the value of current 2, we can use it to help us solve for the first loop. Now we know values for 2 of the currents, so we can plug them in to solve for the last one. The problem wanted us to find current 1, current 2, current 3, and the direction of current 2. Through our equations, we now know all of these answers. Hopefully that practice problem was helpful in learning more about Kirchhoff's laws and how we can apply them to circuits. They can be used in many combinations to solve for all sorts of variables with any number of loops. The easiest way to solve these problems is to assess what you know and then use that to figure out what route to take in solving the problem. Thanks so much for watching.